somebody just asked me this in discussion forums, or it's last night, I guess they did, and but the person's not just not making the connection about significance testing and what it's all about. So I'm suspecting what's happening is, and I'm sure this person's not alone because it's complicated. Way back when we studied normal curves, back chapter 6, I said, go take a look at these things about using the applets and some other ideas. And then as soon as this page loads, and then I suggested that you go watch these 3 videos right here. Now, honestly, the first one's probably the most important one. It's this guy's an AP statistics teacher, and he talks about sampling distributions. This one right here is the one you want to see. It's only 12 minutes long. It's worth your time. I'm going to try to what I do in person when I teach this course is we watch this together, and then I come out here to this applet here, and then you don't need this calculator. This is just a simulation, and what it is here's some population. This happens to be a normal population, but it could be skewed. Now I'll do a skewed one just to see how it happens. So we've got some population with a mean of 16. Here, let's click begin. No, I think I'm here. And what I'm going to have it do is in a sampling distribution, it draws a sample from a population, calculates, in this case, the average, the mean. It could be p-hats. That guy in the video says pile of p-hats, pile of x-bars. We're going to calculate a pile of x-bars and see what shape those sample statistics make when we draw many of them. So here I'm going to do mean. This applet's a little limited because it only lets us max out to 5, but it'll do the trick. I'm going to do a sample of 5, and then I'm going to do a different sample of 25, and it's going to. So let actually just send me yakking. Just let me do it. So here, it's pulling out 5 individuals from that population, calculating the mean and graphing the mean. So that's the mean of those first 5 individuals. This is going to graph the mean of 25 different individuals. And it looks like they're pretty darn close to the same. Okay, let's do another one just to get the idea. So there's 5, graph that, see it's a different mean. And this now do 25. And that's going to graph, and that's also different from the first one. Okay, now if you notice, there's not enough samples to be calculating these statistics. So I'm going to draw 5. I'm just going to have it grab 5 more. It'll automatically jump in. Now that's enough to start calculating mean. The population mean, which this is normal population, has a mean of 16, and this average of 7 samples has the averages of all those sample means. Those 7 sample means is 10.5, which is different. I would call that pretty significantly different from the population mean. And this sample of 25, these 7 samples of size 25, these 7 X bars represented here, they have an average of 11.55, which is again different, kind of underwhelming. Let's draw 10,000 samples. Okay, what I want you to see is the 10,007 samples of size 5. So this graph represents 10,007 X bars. It pulled out 5 samples, 10,007 samples of size 5, and calculated the average of each, graphed them, and then this number represents the average of those 10,007. Notice that's pretty darn close to the population in this sample, and I hope you see that this is a normal distribution. And then when we get samples of 25, a much tighter spread than the samples of 5, and that also basically has the same average. I mean, that's not so much important. What I want you to see is those samples. When I graph all those sample means, they make a normal distribution. This will actually let us fit a normal curve to it, and you can see they're getting pretty close. So normal population, even a sample size of 5 will make a normal sampling distribution. Notice how the sampling distribution isn't as spread out as the parent population. That's because that central limit theorem we looked in chapter 7 or chapter 6 said, and we were using it in chapter 7, using it in chapter 8, says, hey, if you've got a normal parent population, so it's a normal parent population, and then and the mean of all those X bars is the same as the mean of the population, and the standard deviation for all those X bars, standard error, is equal to the population standard deviation divided by the square root of the sample size. So if we look at the standard deviation from the parent population, that's 5, and we're divided by the square root of 5, right? Because these are samples of size 5. Why am I writing 5? Just a minute here. Undo. Square root of 5. Square root of 5 is a little better than 2. 5 divided by something a little better than 2 is 2 point something, and you see how that actually agrees with that. So that's that standard error. And back when we were doing the exam 1 and confidence intervals, you were using this to come up with the margin of error. And then what I wanted you to see, as the sample size increases, the standard deviation for the samples, the standard deviation for all those sample means is a lot smaller than for size 5, and a lot smaller than the population. So that would be 5, same mean, right? Now, then this is still normal. Sorry, I haven't changed gears yet. 25, so that's going to be 5 over the square root of 5, which is the standard deviation of 1, is what theory says. And for these 10,007 samples, it's not quite that much. If I had to do 100,000 samples, it would probably come closer. Well, let's do it. I think I can do it here. Let's grab 100,000, another 100,000 samples. And see now we're graphing 110,007. See how that standard deviation is the same as we want. There's series supports, and the same thing with the standard deviation. Okay, so that's for a normal distribution. Kind of not unexpected that the sampling distribution would be normal, but that's what lets us use very small sample sizes. That's part of that condition check. You can use that T distribution. I'm kind of going into chapter 8 now, or actually chapter 7, I guess, the hypothesis test. We use the T distribution if we don't know the population standard deviation. So if you didn't know that population standard deviation was 5, you'd have to use the T distribution. One of the requirements for that is that you have a normal population and you don't have to worry so much about the sample size. If you don't have a normal population, then you have to have a bigger sample size. N is bigger than 30 is what really happens. So here, let me clear these. How do you clear the lower? Let me clear my writing. And what I'm going to do is now we're going to make a distribution that's very right skewed. Okay, here, let's do that. That's very right skewed. Different mean. Let's have it graph 100,000 samples. So even though the parent population is skewed, we're getting a sampling distribution that's normal. And notice for the n equals 25, that's a very, very tight normal curve, okay? So that's what the central limit theorem says. Because we don't care what the parent population looks like. I mean, unless we're trying to do something with small samples. But we know that the sampling distribution will be normal. In that case, because it's normal, we can apply all the ideas about normal curves to confidence intervals and significance tests. And since this is a question about significance testing, I'm not going to spend a lot of time with confidence intervals on this. I want to jump right to significance test. Okay, so let me stop. I'm going to pull up some. A problem out of the textbook, and we'll walk through that. So I decided first one I'm going to work on is on page 151, number 25, about SAT scores. Now they're telling us that the mean SAT score is 500 and the standard deviation is 100. And then the mean SAT score for all the people that took the SAT test that year was 515, but they didn't tell us the standard deviation. So what he did here, he just didn't want to confuse you with two standard deviations. So, then we read an article for an SAT prep course that states that in a sample of 76 students, the mean math score was 534, which is different from 500, right? In fact, quite a bit higher. I mean, is it a lot higher? I don't know, certainly less than one standard deviation if we use the 100 number. But remember, now we've got a sampling distribution because this is a sample of 76 people. So what are some things I need to do to run this? Well, I know the population standard deviation. I know that SAT scores, since they're standardized tests, they have a normal parent population. So we're good to go with that one sample Z-test is what this is all about. And there are calculators out there that'll do this for you. I honestly run Z-tests by hand because they're not that bad. And this will help you with your question about how is it all related. So what I'm going to do is what am I going to do? I guess I'm going to write on the screen right here. That'll carry along with us. So what are they trying to test with this? Assume the parent population deviation is 100 and test the claim the mean score for prep course students is above the national average of 515. Oh, I see. So these 76 people who did an SAT prep course. Okay. So, about 515. So they changed. So it's slightly different, must be slightly different for that 1 year. The mean SAT last was 515. Okay, so that means we're going to treat the same standard deviation. And then I guess I should read these more closely. Sample of 76 students, the mean score was 534. So here's what we're looking at. If you think back to that applet that I was just looking at, okay, we've got a normal parent population. They went out and did a sample, and we know that parent population has a mean of 515, not the 500. That's the gold standard, and this is what it just worked out to be that year to make it work. And we got a sample of 76 students, and their average score is 534. So 534 here. Let me change this so it's a different ink. How do I do that? Well, here we'll go. Just go here. Here it is. So 534 is up here. And what we want to say, what's the probability of getting a sample of 76 students where the average is going to be 534 or higher? And if we remember back to that test question about selling magazines, what would convince you that more than, well, one test version had 7% of sales to convince you that 7% figure is too low. What we're trying to do here is this far enough away? The probability of this happening, is it small enough to say that the average for SAT prep course students will be higher than the national average for all students? So that's what the claim is, right? In fact, let's underline the claim right here. Or can I do even fancier and highlight it? Let's see, draw. Where's the highlighter right there? I don't know if this highlighter works very well. Well, let's see, it's red. Let's do it. Let's see. So we're going to test the claim that the mean test score for prep students is above the national average of 515. So we know the center of this distribution is 515, right? So HO, null hypothesis. Nope, the average test score for these tests prep students is the same as the national average, and any variation is just due to random selection, random sampling error, right? And then the the alternative hypothesis, no, indeed, they do better than 515, and this is going to be far enough away from the 515 to say that it's something different. It's significantly different, statistically significant. One thing I want to make sure you point out, I was helping somebody yesterday and there's a little confusion there. This number and this number will always be the population mean, or population proportion if we're dealing with proportions. Okay, so now we've got to calculate, and we've got a sampling distribution. Because we've got the sampling distribution, the population average is 515, and the standard deviation for the sampling distribution, well, this is writing weird, huh? Is equal to the population standard deviation 100 divided by the square root of the sample size. So 100 divided by square root of 76 is, I don't have a calculator right here, just a minute. So on my calculator, I got a standard deviation of 11.5. I'm going to round pretty liberally since I'm not trying to make WebAssign happy or MyOpenMath happy. So that standard deviation for the sampling distribution is about 11.5. Okay, so what I'm trying to do now is I need to get I made the claim. Oh, you know what I should address, which is the claim. So here's the claim. This is the claim that their SAT prep students do better than everybody else. So here, can I change my ink to, I'm going to go to green here. So this is the claim. And that's the hypothesis that represents the claim. Okay, so I've got my HO, I got my HA, I know my standard deviation I need. I know I want to see that it's bigger than 534. So in the next test is to get a test statistic. And all the test statistic in this case is a Z-score. And if you remember back from our work earlier, we're going to take the 534 because that's the number we're interested in, minus the population mean of 515, divided by that standard deviation for the sampling distribution, not the 100, but the one for all the samples of size 76. Now, what is that? That's going to be 19 divided by 11.5. Let me make sure. It's early in the morning here. 534 minus 515. Yeah, 19. I'm divided by the 11.5. Okay, so I'm getting a Z-score of about 1.65. Okay, so that's the test statistic. Now, p-values, I mean, we go find a critical value of Z, but honestly, the p-value is more useful, I think, often. So what I'm going to do is find that probability. I'm going to find that red area probability. Now, I could go to the normal table in Dr. Stevens' textbook. I would go down the right column. Well, you know what? I think I've got the book right here. Let's just do that. Let's see, what page is this? This is page 151 or 153. Let me go down. Let me get a pointer. Come down to the normal table. And I'm going to look for where's it? 1.65. Yeah. So I'm going to go 1.65. Here we go. I know I'm sorry about all the writing, but I don't want to erase it all. I'm seeing that's the area to the left. See how actually that lined up kind of nice. The table always tells us the area to the left, and we want the area to the right. So we got to take 1 and subtract that 0.9505, which I probably could do in my head, but 0.9505. So that's giving me 0.0495 in my pen. So that's the p-value. That's that red area right here, right? That red area is 0.0495. Come on. 0.0495. Which, did they give us a level of significance on this? Let's see, where it was on page 151, I said here, 153, 151, wasn't it? Come on. I don't want to erase all my writing, so we're going to have to read through it. I hear the SAT thing. So did they tell us? See, they did. They said a 5% level of significance here. Let me get a pointer so you can see that. See, they said a 5% level of significance because my p-value is less than 5%. That means I'm going to reject HO. This is far enough away from that mean of 515 to say that something statistically different is happening with those students that are taking the SAT prep course, at least for this sample of 76 students. Okay, so we reject HO, and then let's go figure out how to write a concluding statement. So for this one, I think it happens here. Here, let me write down. I'm going to write down some stuff so I can go. I'm going to show you how to use the applet also. Actually, I won't. I do have an applet, but I like I said, this is pretty straightforward, so I'm not going to run an applet for this. You can. I've got one linked if you want to play with it. But we do want to make our concluding statement. Let's see. Well, here, you know what? So Let me do some cleaning up here. No, I don't want to erase everything. I just want to erase that. It won't let me. Okay. All right. That's okay. Oh, there it is. Here, we're going to erase some stuff. We're going to erase this stuff. Erase that. I know watching me have to, I should pause this, huh? After that. No. Okay, so let's go look at those statements. That little box here. Here it is. So HA was my claim, or H1 was my claim, right? So because I rejected HO because that p-value was smaller than 0.05, we're going to say the data supports the claim that the mean SAT score for students who complete that SAT prep course is higher than the mean for everybody else. Okay, you don't want to. So you don't want to be. You want to be careful about saying, "Yep, SAT prep courses work. We should go do them," because this was a sample of 76 people. Who knows if it was a great sample? It might not have been a representative sample. So statisticians, and you should, if you start using data for this, you need to hedge your bets. Say the data supports the claim that you don't want to just say, "Yeah, it works. Do it," because you want to be careful with those conclusions, drawing conclusions like that. But that's how you use that table to come up with the wording. There was one other thing I wanted to say. Oh, the other thing you got to worry about, because I'm going to ask you, you're going to see some stuff on the quizzes and on the cookbook exercise. If you've done those, they don't always have a level of significance. So the rule of thumb I read somewhere, it said, if somebody's going to die or lose a lot of money if you make the wrong decision, go with a level of significance of 1% or 0.01. If it doesn't matter so much, 5% is fine. Okay, with this, people are going to lose money if they pay for the SAT prep course. I don't know. I guess if I was the people trying to sell the SAT prep course, I would use a 5% level of significance. I mean, if I was a parent group trying to caution parents, I would go with a 1% level of significance, and I would change my conclusion. Especially because this is pretty close to 5%, right? So it depends on what they're trying to do with it. So that's a one sample z-test. What happens if we have a t-test or a proportion? Let me pause this. I'll get one ready, prompted up for you. Now, I probably made a video about the corn, but I'll go with it again. So Farmer Carl says that less than 15% of his ears of corn have worms in it. So we're going to test his claim. So I don't see any mean. I don't see any standard deviation here. So I'm going to use one sample, one proportion test. Okay, and it's a z-test. It's another z-score calculation test statistic. And what I need to know is I need to know my P sub O, my. So what's happening here is I've got this distribution. We know it's normal because it meets. Well, the condition we got to meet here is 0.15 times 80. Is that larger than 5? And it is. So it passes that. Then we're going to say, is it 1 minus the 0.15 times 80? Is that also larger than 5? Yep. So you use this condition check back in chapter 6 when we did that normal approximation to the binomial distribution, the last section in that chapter. Now we're kind of leaving the normal approximation alone, but we're going to use that to run this test. So here we're going to run a proportion. So we're going to deal with by the number of successes divided by the total. And he's saying on average that 15% of his worms ears don't have worms. So HO, so that means 0.15 is the middle. And we might be wanting to show that it's higher. I mean, maybe we're some consumer group want to safeguard the public and see if cars lying to us. We'd want to say that, well, let's set this up. So HO P equals 0.15. We can't say that we could go with a two-tailed test, but since he said less than, we'll go with a left-tailed test. And what I'm going to do is before I do this, I'm going to calculate the p-hat. What happened from the sample proportion. So he got 6 out of 80. And 6 divided by 80 is, let's see, 4, 4 out of 40. No, 3 out of 40, which is, I don't have a clue. 6 divided by 80. So I'm getting 0.07. I'm getting 0.075. So we're trying to show that, that sample result of 0.075. See, he's claiming that less than 15%. So this kind of would support his claim if that was true. All right. So what we'll do for this one is we'll say, we'll make it a left tail test. Sometimes if your p-hat's too large, larger than your middle, then you got to make it a right tail test. And that just comes with starting to look and see, see how we calculate the p-hat first. I wanted to make sure that it was going to be lower than the mean, lower than the middle. Well, that's going to be 0.0. Dan LeMay, what are you doing? I just said you want to make it be the same. So here, just a minute. Give me a second to get caught up here. So we want to say that P is less than 0.15. Okay, now to do this by hand, let's see, what do we want to do? Well, we got to calculate a standard deviation. We know the mean. The mean is the middle, that is at 0.15, and we got to get a standard deviation for those proportions. So here, let me make a little white space here. And to get the standard deviation for this, so the standard deviation for all these p-hats, pile of p-hats, is going to be 0.15, the population mean, the number we're using in hypothesis tests, times 1 minus that, over the size of your samples, which is 80. And I'll take the square root, and then I'll just crunch that on my calculator off screen. So 0.15 times 0.85 divided by 80, and then I'm going to take the square root of that. I'm getting 0.0, I guess 0.04, you'll round to. So that's my sample, that's my standard deviation. So now we're going to get the test statistic. That's a z-score in this case because it's a one prop z-test, one proportion z-test. So now the number we want to compare to the mean is the 0.075. We're going to subtract the population mean, or population proportion, 0.15, the number that we have there. And we're also going to divide by that standard deviation, which used the 0.15 as the p, right? So that's going to be negative 0.075 divided by 0.04. Let's see, so 0.075 divided by 0.04. I'm getting a z-score of 1.88. It's 7.5, but that's and it's negative, sorry. Yeah, it's negative z-score. So now we're going to go get the probability of getting a z-score that small. And notice that that the p-value, that the area we want is a left-tailed. So we just can take that value right from the table. Let's go to the normal curve table. And then we're looking for a z-score negative 1.88. So here's the negative 1.8 line. Come over there to 0.0301. So that's our p-value. I guess I should write that down so we can go back and make a conclusion. So the p-value, that area there is 0.0, what did I say? 0.0301. Now let's go check out the level of significance. I think it's probably a 5% level of significance. That would make sense in this situation. Let's see here. Problem set, and it's down around page 50. It wasn't that far, was it? It was right off the top because it was proportions. Test the 5% level of significance. So we would reject HO because that p-value is smaller than 0.05, and then we can go get that conclusion. Something the data supports a claim that less than 15% of his earworms, his corn of earworms. Then what's interesting in part C or part B, you see how we're doing a smaller level of significance, 0.01. Well, that point, our p-value is not smaller than 0.01, so we would fail to reject HO. And this is one bad thing about significance tests. You can change the decision just by going with a smaller p-value. And there are limitations to it, but this is one of the tools we can use to make inferences about data, and it's not infallible, but this is how you can tell the difference. And that's what was it that you could apparently why was it contradictory? Because you just took we had a higher threshold or a lower threshold of saying something different. Okay. And like I said, if people are going to die or lose a lot of money if you make a wrong decision, you want to go with that 0.01 significance level. And if it doesn't matter so much, 0.05 works. Okay, now before I leave this problem, you knew I was going to do this. I want to do go to a calculator instead of doing all this by hand. Because next week you're going to want to be using calculators. I mean, you can do the formulas there and possibly hard, but I think some of you will certainly appreciate being able to do them. You use the calculator for it. So the calculator I'm going to point you towards is that Rossmann chance calculator, and that's in let's see, can I get there from here? Let's see. Sometimes I don't want to lose everything that I have here. Modules, and then those online tools. Where are we? Come on. Course resource, it collapsed on me. Online statistical tools, and I want it to come down to inference. So here's that link to that one sample z-test that I talked about. It works pretty well. I just want to do it by hand. Then this one down here takes us out to that Rossmann chance website. And it works for one sample test that we're doing this week, chapter 8, and next week, the 2 sample test. And we're out here. Now, this is about a proportion. So make sure you do the right drop down. One proportion, we have a sample size of 80. We had, oh heck, what was it? Let's see. We had 6 out of 80 ears of corn. So I'm going to do, the count was 6. We're going to calculate. Calculated the p-hat. We did that. We're going to do a test of significance. We got to set up our HO and H1, and those were 0.15 and then less than 0.15. It automatically catches it. And you've got to change to a right-tailed test or a two-tailed test. You got to click on that. It calculates it for you. There's our test statistic. There's that p-value. See how it matches? This one matches perfectly. So all you really have to do to make me happy is write HO, write H1, identify which is the claim. Oh, run the condition check. Make sure you've done the conditions because you know that you're running the right test. And make sure you identify the claim. And here we get a very small p-value or a p-value less than 0.05. So we're going to reject HO, yada, yada, yada. So it's that easy. Okay, so now I'm going to do one more problem, and I'm going to go, instead of calculating it by hand, I'm going to show you, I'm going to go right to the applet because it's going to require t-scores. Okay, so let me clear all my writing. Let's see here. And then I'm going to come back here. And then I'm going to go to the section here where we don't know the population standard deviation. Now, you remember those conditions I was talking about in the beginning? I've looked at this sleep problem a lot. I don't want to do it again. Let's look at the assembly time. Why not? I haven't done this in a while. So a group of 40 adults or 40 grown-ups, a mean assembly time to put together a swing set was 1.78 hours with a standard deviation of 0.75. One thing I'm noticing here is that this is coming from a sample. That's not a population average. That's coming from the samples. That's X bar. That's the standard deviation for the sampling distribution. Oh, no, that's the standard deviation for the sample, not for the sampling distribution. The makers of the swing claim that the average assembly time is less than 2 hours. All right, so here we go. I know this. So what happened? I have no idea. I know this is about means. I have no idea about the shape of the parent population, but I do have a sample of 40, which is more than 30. So we're good to go with the central limit theorem using this technique because we have a sample bigger than 30. So HO well, actually, let's identify the claim. They kind of told us right there, so I won't make too big a deal about that. But that's the claim. So we'll say HO, the mean assembly time is 2 hours, and and just because these people took less than 2 hours, it's just due to random sampling error, right? Random sample change don't always produce the same results as the population, but we know from confidence intervals they can be within an acceptable range. So now, because they said less than 2 hours, I know this will be a left tail test. And because the sample mean is less than 2 hours, I know it's a left tail test. Okay. Now, before I go to that applet, I am going to show you one more thing. If you're going to do this by hand, so you're going to run a t-test, not a z-test. This is a t-test to get the test statistic because we don't know the population standard deviation. So we gotta come here, eraser work. So I'm going to write a t-test, and what I would do for the t-test is I would take the 1.78 minus the 2, and then you got to do that sampling distribution standard deviation, the 0.75 from the sample, that's where we're going to use the best estimate of the population standard deviation. 0.75 divided by the square root of 40. And then we'd have to calculate all that by hand and come up with the t-score. Then go look up the t-score in a table, t-table, find the tail area, a little more involved than the z-score. So let me show you this applet. I need to remember, let's see, before I leave this page, I think I've got everything there. I've got X bar, see, I've got X bar equals 1.78. I know the sample standard deviation is 0.75. Notice I'm not really worried about the answer to that calculation. Applet will do that for us. Let me erase some of this stuff. One other thing I neglected to do is this is the claim. Okay, let me erase this stuff so we can have a big, nice, clear view of that screen. Okay, so now we're going to go to back to Rossmann chance. Here, because we're about one mean, you got to make sure you select one mean, and then see how it asks you sample size. Our sample size was, oh crap, was it 40, wasn't it? 40, Dan. And then our sample mean is 1.78. See, it needs the sample size to calculate that standard deviation. Okay, and we do a choose test significance. We're going to make it be 2. Notice the way the symbol is mu for when I just have one mean selected. And when you want to go less than 2, just like we did here, we'll calculate it. There's our test statistic. There's the p-value. At the 5% level, we would reject HO. So the data would support the claim that the mean time is less than 2 hours. So how does that test statistic relate to that mean of 2? Well, it's far enough away from the middle to say that yes, something statistically different is happening. So we don't feel that the stated mean, the claimed mean of 2 is accurate. Okay, so I hope let me come back here to that slide and let me make sure that we are address the questions that you asked. So let's see. Null hypothesis, test statistic, and p-value are all connected. I'm hoping that what I've shown you here is how this works. So the null hypothesis says there's no difference. The research or alternative hypothesis says there is a difference, and we got to go with the direction. The test statistic is basically how many standard deviations away from the mean, and the p-value is the probability of getting a test statistic that far away. Okay, and then we talked about how to reject HO. I'm hoping this is helping for you. Certainly, if you want to look at some work, you can go look at anything with a starred exercise. You can try it and go look at Dr. Stevens will throw you the book, the text, the tables, the manual way of doing this versus the applet. But you can certainly run the applet and see if it agrees with his answers. Okay, so again, that applet is this Rossmann chance applet. You're going to find that right here in modules, course resources, that online statistical tools. And this is the one for confidence for t-test and one proportion, and then this is the one for one sample z-tests if you want to go that route. Okay, so give me a yell if you need some help, and post some work in the discussion forum if you want to check it out. You know, those cookbook problems are good to use. Probably a long enough video. Let me know if you need more.